in the last two videos, what we've been doing is we've been working with something called an RC circuit, and that's basically what's shown right here. Okay, but up till this point, we've just seen a bunch of formulas. We haven't really seen how they work together. What we're going to do in this video is we're going to keep this right here in mind, and we're going to work some fairly straightforward problems that you can see in your instrumental class. Okay, so right here I have a problem, and what we have is we're given a resistance for the resistor. It's 15 times 10 to the third ohms. We know the capacitance is 8 times 10 to the negative third farads, which are the units of capacitance. And we know that the input voltage of the battery is 20 volts. And there are several things that we have to calculate. Number one, we have to calculate the time constant. And the time constant is basically just the resistance times the capacitance. We also have to calculate instantaneous quantities for current, voltage across the capacitor, and voltage across the resistance. Okay? And number one, we're going to use these formulas that are right here to do that, but also we're going to do it where time is equal to 4 time constants. Okay? And so what that means is that 4 time constants have elapsed since we started it. Okay? So time is equal to 4 RC. Okay? And in general, I mean, if you knew the resistance and the capacitance, you could plug in any time value there. You could plug in, 10 seconds or whatnot. But the whole point is that we're just going to make the math really easy here. And what we're going to find is that resistance and capacitance actually cancel out. Okay, so this is just a nice case, but just know that you can plug in any time you want there. Okay, so the first thing we want to do is calculate the time constant because that's part A. Okay, so what we're going to do is we're going to use the formula: the resistance times the capacitance is equal to the time constant. Well, in this case, what's the resistance? Well, the resistance is going to be 15 times 10 to the third ohms, right? That's the resistance. We're going to multiply that times the capacitance. In that case, it's 8. Since I'm running out of room, actually, let me just go ahead and do this. 8.0 times 10 to the minus third farads, okay, minus third farads. And when we multiply these out, we should get units of seconds. So your time constant is always going to be in units of seconds. So when I multiply this out, I get that the time constant is equal to 120 seconds. So that's our time constant. We'll put a box around our answer. Okay. And so now what we want to do is we want to figure out the instantaneous values for 4 time constants when that time has elapsed. Okay. Now notice what appears in every one of these equations for the instantaneous current, the instantaneous voltages, and so forth. We have this term right here, and I'll do this in orange. It's this negative T over RC. That's in all of the terms. So what I want to do now is, since it's in all of them, and I'm going to have to find it, I might as well figure out what that argument of the exponential function is. So let's actually calculate negative T over RC. Okay? And at first, you might just be tempted to plug in, RC is equal to 120 seconds in the denominator. But notice that our time is just 4 RC. Right? So let me just plug that in and I get negative. Well, time is just 4 RC. 4 RC. My denominator is RC, so notice that the resistances cancel out, the capacitance cancels out, so the argument in my cosine function is just negative 4, right? So that means that in all of these equations, I'm essentially going to have it's going to be exponential of negative 4. Now let's actually go about calculating our instantaneous current. That's our first instantaneous quantity that we want to calculate. But the problem is, to do that equation, we're going to need the initial current. Okay? And to do that, we're going to have to use this bottom equation, which says that the voltage across the battery is equal to the current times the resistance. Okay? Well, so we have voltage is equal to current times resistance. Okay? That's just Ohm's law, right? So how do we isolate current? Well, we divide both sides by the resistance, right? So now we have that the voltage divided by the resistance is going to be equal to the initial current. Okay. Now, this is the initial current, and what we can do is we can actually substitute it into the equation for the instantaneous current. So what we can say is that the instantaneous current is going to be equal to the voltage divided by the resistance, okay, and that's the initial current basically, okay, times exponential. Well, we already found what the argument of the exponential function is. That's just negative 4. This is exponential negative 4. And we can plug in numbers now, okay? The voltage is 20 volts, okay? The voltage is 20 volts. The resistance is 15 times 10 to the third ohms, okay? And then we multiply that times exponential of -4. And what that leaves us with is a current of 2.4 times 10 to the -5 amps. And so when you divide voltage, or volts, divided by ohms, you get units of amps. So this is going to be our instantaneous current when we're at 4 time constants, when t is equal to 4 RC. Okay, and we put a box around our answer. Now let's actually find the instantaneous voltage about the capacitor. Okay, so what we're going to do is we're going to play a similar game, except we're going to use the initial voltage. Okay, so the instantaneous voltage about the capacitor is going to be equal to the input voltage of the battery, the input voltage times the quantity 1 minus e to the -4th, okay, or exponential -4th. Okay, so we start plugging in numbers. What's our initial voltage? Well, our initial voltage is just 20 volts, right? And is 20 volts, and then we just multiply that times 1 minus e to the -4th. Okay, now e to the -4th, okay, that's a pretty small number. And if you have 1 minus a really small number, it's not going to be that far away from 1. It's going to be less than 1, but not that far. So we would expect, in this case, the voltage about the capacitor to be just a little bit less than 20, and in fact it is. Okay, when we actually calculate this out, it turns out that the instantaneous voltage about the capacitor is going to be 19.64 volts. 19.64 volts, and that's going to be the instantaneous voltage about the capacitor, and then we put a box around our answer. Okay. Now, assuming you found the voltage about the capacitor instantaneously, and you need to find the instantaneous voltage about the resistor, there's sort of two ways to go about doing it. Okay. The first way is to actually just calculate it directly. Let's actually do that, and then we'll go back and look to see if there's any other ways. So the instantaneous voltage about the resistor is going to be equal to the input voltage times exponential. I'll go ahead and write it like this, exponential -4th. Okay, we already found what that quantity is. So we plug in numbers, and we find that it's 20 volts multiplied by exponential -4. And since exponential -4 is a really small number, a really small fraction, we're multiplying by 20. It shouldn't be a very large number because exponential -4 isn't very large. Okay, it's closer to 0, in fact. And so when we calculate this out, we get a value of 0.36 volts, and that's going to be our instantaneous voltage about the resistor. And we put a box around our answer. Now, what I mentioned is there was another way that we actually could have found the instantaneous voltage about the resistor, assuming we knew V sub C. Okay, keep in mind that our initial voltage was 20 volts, right? And what did we say in a previous video? Well, we said that the input voltage had to be equal to the instantaneous voltage about the capacitor plus the instantaneous voltage about the resistor. So what this equation would essentially become, and I'll do this in red, is our input voltage was 20 volts, right? And that has to be the sum of the two instantaneous voltages about the capacitor and the resistor, respectively. So we knew that the voltage about the capacitor instantaneously was 19.64 volts, right? And you add on to that the instantaneous voltage about the resistor. So you could subtract 19.64 volts from both sides, and that would give you this value of 0.36 for the instantaneous voltage about the resistor. Okay, so if you know your input voltage, which you should, okay, and you know one of these quantities, you can actually just subtract it from the input voltage to get the other instantaneous voltage. Okay, and we could have solved for the voltage about the resistor first, and that actually probably would have been easier because we wouldn't have this 1 minus e to the -4th. It would have just been exponential -4th. Okay, so there's multiple ways to go about doing this problem, but this is a fairly typical problem that you'll see in your introductory instrumental analysis class. So I hope this video gave you a little bit of intuition on how to work these problems. See you in the next video.